This is the online lesson number 2 for Algebra 2. Today we're going to be exploring different rates of change. Please go to the Tower of Hanai website and play with that game. It should remind you of a children's game of stacking rings. Play with different combinations starting at 3 rings, go up to 4, 5, and notice what's changing. As we come back together, we'll realize that at 3 rings, we had 7 moves, 4 rings, 15 moves, 5 rings, 31 moves, 6 rings, 63 moves. We could also try to calculate when and how many moves when we have 7 rings and how many moves when we have 10. That's what we would want to answer for this. We're going to go through this in the Zoom meeting using Desmos to see if we could figure out what's happening. One thing we should realize is that this rate of change is not constant and we have a new situation. That new situation is called exponential functions. We can either increase at an increasing rate or decrease at a decreasing rate depending on what our situation represents. Here's what the function looks like for exponential growth versus decay. Again, let's remember with negative exponents that we turn those into fractions. We move the negative power to our denominator and then we square it. So at -2, we've got 1/4. At 0, anything to the power of 0 is 1. At 1, we're at 2, and then we grow up from there. You can see how that is represented on the graph. As we go back in time, we will always stay positive, although we will be getting a smaller and smaller fraction. Some of the characteristics of an exponential function is that it's increasing at an increasing rate. That means the difference between the points from here to here is going to be less than the difference in the points here to here and less than the points from here to here. So every x you increase, your y is increasing at an increasing rate. Our domain is all real numbers. Your range is y greater than 0. Notice I did not say greater than or equal to 0, but just greater than 0. And we have a new definition of a horizontal asymptote. An asymptote is a line that your graph approaches but never crosses it. Think about it like an electric fence. Your graph is going to be approaching that electric fence as we go back into that negative region, but it's always going to stay a fraction that's positive, even if it's a very small and ungraphable fraction. Here's the graph of 2 to the power of x. Again, you can see that represented versus the graph for 3 to the power of x. As we're looking at this and we're trying to identify what our rate of change is, again, notice that both of these have a point at 0, 1, but that first point is at 1, 2, and this first point is at 1, 3. That next point is going to be at 2, 4, and that other point is going to be at 2, 9. That should help you see what that base is. If you think about 2 to the power of 1 versus 2 to the power of 2, and think about 3 to the power of 1 and 3 to the power of 2. That helps you see how those values are increasing at an increasing rate and helps us identify the difference between the graph and the base between 2 to the power of x and 3 to the power of x. As we're looking at these functions, all exponential functions are going to take on this form in a simple version of just b to the power of x, where b is always greater than 0. The domain for these functions is all real numbers. What I really wanted to point out on the slide is that if b is greater than 1, the graph is increasing, similar to the first figure on the left. And if the function is less than 0, some sort of fraction, then it's exponential decay. And the graph is going to fall to the right. Both of these have a similar range in that all of them are going to be greater than 0. The exponential functions in their simplest form are going to take on this idea of a times b to the power of x. In this situation, your a value is your y-intercept, and the b is your rate of change. Here are a couple examples for us to look at. We want to identify the y-intercept and the rate of change for these functions, and then finally decide if it is growth or decay. Again, that value at the beginning of the function is your a value. That's going to be your y-intercept. So for this first one, our y-intercept, again, your y-intercept is a coordinate, and you want to write it as a point. The growth is this b value right here, which is 1.03. Now technically the b should be equal to 1 if this was a constant line, so actually the rate of change is 3%. And when we're dealing with these problems, x is usually going to represent time up here in our power. When we look at the next question, again, your a value is at the beginning, therefore your y-intercept would be 0, 10. This b value is less than 1, which means that this is exponential decay. Looking at the next one, again, your a value is that number in front. Always write it as a coordinate. The b value is the 0.75. That number is less than 1, which again would make this decay. Now in our first couple examples of these functions, again, we're looking at whole numbers here. On the last example, we have an a value of 15. That means our y-intercept is the 0.015, and that b is 3. Because that b is greater than 1, it's exponential growth. Again, we want to pay attention to that a value and the b value. That's going to help us predict what type of function we'll be looking for. When we're looking at these, again, we want to think about this idea of growth versus decay. Here's our two situations that we can use to model growth versus decay. In both situations, a is going to equal the amount either in your accounts left after a certain period of time. P is your principal, your initial investment, or your initial value. So that could be bacteria, that could be population, that could be money in a savings account. It's kind of that initial investment. Our R is the rate. A lot of the times the rate is going to be given to you as a percent, and it's going to be your job to convert that to a decimal. And then T is going to be time. On the situation on the left, we're taking 1 plus R. That's going to be how we represent the growth. The 1 represents your 100% of your population, and then you're adding to that the rate. For the situation on the right, you're going to do 1 minus to get your value less than 1 to give you your exponential decay. So you have your 100%, and then you're taking away your rate. When doing this, you want to think positive and represent what you have left, not what you spent or what you've lost. So here's one of our situations. We're going to deal with $1,000 in a savings account at 5% interest. So your A value, that initial investment, is 1,000. Your B is not 5, but your B is the 100% that you would normally have plus your 5% growth. So that's 105%, which as a decimal is 1.05. So if we want to write an equation, we would write an equation of 1,000 times 1.05 to a power of t. So if we want to figure out how much we have after 4 years, we're putting in 4 for our time, and we're going to solve that mathematically. If you want to figure out how much you're going to have after 16 years, you're going to plug that in. And that's going to tell you how much your investment is worth over time. In this situation, we're spending 15% each month, again, starting at that initial investment of 100 or 1,000. So you have to think about your 100% minus your 15% that you're spending, you 85%. So when you're using that as a decimal, it's 0.85. So your equation is 1,000 times 0.85 to a power of t. If you want to figure out how much you're going to have after 10 months, again, that's your time, so you're putting in a time of 10 months into that value. Now, on the last question, it's going to require us to do a little bit more math. We want to figure out when our account would be down to $1. The last situation, we're trying to figure out when our money would be down to $1. So this time my answer is 1. And I'm solving for time. This is going to require us to do a little bit additional math that we don't quite have the skills yet to do. We would have to rely on our calculator in order to actually solve this, but we will get into using the calculator a little bit more soon.